So in this video, let me show you how to do some example of calculating the component forces. So a force can be acting on an object on different direction. It can be acting on an object on this direction, or on this direction, or on this direction. Okay. However, we can always break the force into a horizontal component. Okay. For instance, for this force, I can always, let me just label it. We can always break this force to a horizontal fx component and a vertical component, so that force is always equals to the sum of its horizontal components plus the sum of its vertical component. Okay. So if I do the same thing, for this one, I can always have fx, I have fy. Okay. That's what we did with vectors before. Okay, so let me give you an example. Say if I have, say, a force acting on an object, acting on a mass, on an angle of, say, 60 degrees. Now, what I can always do is, I can always break this force, say 100, well, let's make it 100 Newton force. I can always break this 100 Newton force into fx and fy, horizontal vertical components. Okay. Now here is the mass part. What we're going to do is we're going to use trigonometry, your so-called toy. Okay, sorry, I think I made a mistake. Yep, so-called toy. Equations with sine, cosines. However, just remember an easy, simple way. Okay. It just makes your life easier. For the horizontal forces, the horizontal component is always equal to the original times cosine theta, cosine cos of the angle. Type it in your calculator, you'll find the amount of horizontal force it is. Remember, unit is in newtons. For vertical forces, it's always a force times by sine of the angle for the vertical part. Okay, so yep, put it in your calculator times, do this. Okay. Or the other way to remember this, now in a triangle, we have the hypotenuse, we have the adjacent, and we have the opposite. The value of the adjacent is always hypotenuse times cosine. Adjacent is hypotenuse times the cosine of the angle. The value of the opposite in a triangle here is always the hypotenuse times sine. Okay. So, yep. Okay. Just remember SO, sine for the opposite components, hypotenuse times uh, sine, okay, hypotenuse times sine of the angle. For the adjacent, hypotenuse times cosine. Okay. For the tangent, well, you need to use your trigonometry rules to find it. But just remember this two shortcut. It helps. Okay. Now let me show you another example. Okay. Now look at this diagram. I have a mass is hanging from the ceiling, and the other side is attached horizontally to a wall by a steel bar or something. Okay. And here I have a rope also hanging it from a ceiling. Okay, on an angle. So the idea is let's find out uh, how does the force distribute on the system. Okay. Assume the mass is stationary. Assume the mass doesn't move. Okay, doesn't move. So what's happening is, yeah, I will have a net force. Well, sorry, not net force, a weight force going down. Okay, which is mass times gravity. Okay, now in order to keep this mass, this mass stationary, I should have in the opposite direction. I should have a force acting upwards. Okay, so let's name it F1. Okay, because okay, now just remember this force, the F1, is not the normal force because the object is not in contact with any surface. So in this case, there will be no normal force. Okay, I just name it F1. And well, because the system is stationary, okay, so F1 must be the same as the weight force. They must be the same. Okay. Now, have a look at the rope. Okay. On the rope, okay, the force, okay, the rope applied to the mass should be in this direction. Okay. However, F1 is on the vertical direction, so F1 must be a component of this force, FR. Okay. So, well, yep, FR for rope, F rope. Okay. So in this case, okay, we know one component, we know the angle from your trigonometry rules, we can find F rope. Okay, remember the idea we used here? Well, you can just let me redraw it. Okay, so we have F1, okay, I have F rope, and there must be another force, say whatever, but what we're interested is this. Okay, and the angle is 30 degrees. So we have the adjacent, and we have the hypotenuse, we have the angle, so we use cosine. Use your so-called tool. So, yep. So, yep. So the idea is the F rope, which is the hypotenuse, okay, should be the same. Sorry. Let me just redo it. Use your soccer toy. Okay. Use your soccer toy. Cosine 30 degrees must be the adjacent F1 on F rope. Okay. So the force applied to the mass by the rope will be F1 divided by cosine 30 degrees. Okay, just use the equation of your soccer toy. Yep. which is mj cosine 30 degrees. Okay. Yep. If you know the mass of the object, you can find the force on the rope. Okay. Now, have a look at this scenario. Okay, we have found the force on the rope. Okay. The force on the rope not only pushing pull the object against gravity, but it also pull the object to the left. Okay, given the whole system is stationary, so there must be a force pulling it to the right, okay, to cancel it off. Okay, so it must be on this steel bar. So I name it FB, okay, on this bar there. Okay, so if you want to find the force acting on the object by this steel bar on the right, it must be same as the horizontal component of F rope. Okay. F bar must be the same as this horizontal component on the rope. For horizontal components, not for horizontal, for the opposite components. So that's a sign if you do your trigonometry. So you have F rope times sine 30 degrees. Okay, so which is going to be F rope is this sine 30 degrees, sorry, divided by cosine 30 degrees. Remember, this is your F rope. Okay, I just put it in. Okay. So you have sine divided by cosine. If you do your math, well, basically after this, just type it in your calculator. Otherwise, if you have sine divided by cosine, for those doing math method, you should know it is tangent 30 degrees. Okay, you don't have to know this, but yeah. Okay, but if you're doing math method, you should know sine divided by cosine. The angle are the same. They should be tangent. Okay. Now,